This Zoom session is being brought to you by the fractal Heart of Gold forming. Right. All right. We go on. Ninth section is vectors. Okay, a vector. It's a displacement in space. It's a motion. Think of it as a motion from an initial point to a terminal point. So it's generally viewed as a little arrow. It can denote displacements. It can also denote velocities or accelerations or forces or fields. So it's all over physics. All right. Now, vectors are equal if they have the same length and direction. These have the same direction but not the same length. These have the same length but not the same direction. These have the same length and direction, close enough, and they're considered equal even though their initial points and terminal points are different, but the displacement between the two is the same in all these cases. Now we can visualize a vector as going from here to here, initial to terminal point. You move a distance a in the x along the x-axis and b along the y-axis. So it's denoted a by b. This looks like point notation with these little brackety things here. Angled brackets says it's a vector. These are the rectangular coordinates for a vector. The x coordinate and the y coordinate are a and b. If you have vector, if the initial point is x1 by y1 and the terminal point is x2 by y2, then the x component of the vector is x2 minus x1 here, and the y component of the vector is y2 minus y1 here. All right. Given a vector a by b, it has a length denoted by this little, looks like an absolute value sign, and the length of the vector is the square root of a squared plus b squared. That's in accordance with Pythagoras. And it's traditionally used to denote a vector either with a little arrow on top of it or in boldface. Now there's an arithmetic of vectors. You can add, subtract, and vectors and multiply them by numbers. You add the vectors this way by what's called a parallelogram rule. If vector v and vector w make their initial points the same, then put another copy of w over here from the terminal point of v, and another copy of v here at the terminal point of w. These should meet at a point, and you get a parallelogram. And the vector u plus v is from the shared initial point to the new terminal point. That's the geometric way of looking at adding vectors. The algebraic way is in terms of the components. A by b plus big A by big B is a plus big A by little b plus big B. So you add components to add vectors. Add components in parallel. Likewise, you can multiply a vector by a number by changing its length. If this is vector v, then 2v is in the same direction, twice as long. A half v is in the same direction, half as long. Minus v is the same length, but in the opposite direction. That's the geometric way of looking at it. And the algebraic way is that k times the vector a by b is ka by kb. And so here, as in here, we do things parallel by components. So now, since the vector addition, in each of its components is just a plain old addition. And so it has many of the same rules as addition. For example, it's commutative. V plus u is u plus v. That's commutativity. It's associative. U plus the vector v plus w is the vector u plus v, that plus w. If we define a special vector 0 by 0, that's a vector with 0 length, and I suppose you could put it in any direction. It plus any vector u is a vector u again. So it acts like the number 0. And u plus its opposite is a 0 vector. Everything looking a lot like ordinary arithmetic. Here we have distribution. If you have vectors u and v and add them, then k times that is k times u plus k times v. So this is called a scalar, by the way. It determines the scale of the thing. So scalar multiplication distributes over vector addition. And we have a similar rule for k plus h times u is ku plus HU. So it's so the U distributes over a scalar sum. And we have a kind of associativity. K times HU is KH times U. There are a couple of special vectors. The vector in length 1 in the x direction has components 1 by 0, and it's called I. The vector of length 1 in the y direction has components 0 by 1, and it's called j. And you can prove from the rules already given that a by b is ai plus bj. So these are two ways of saying the same thing. Now, since this is a trig course, we have to talk about angles. And there's another way of looking at vectors. They're called polar coordinates. Given a vector v, we'll talk about its, we can suppose we know its length and the angle it makes with the positive x-axis. Then the vector v can be thought of as the vector length times this special vector cos theta by sine theta. This is the unit vector, the vector in the same direction as v, but with unit length, cos theta by sine theta. That's sort of like the polar coordinates for complex numbers. In fact, very much like it. Okay, so for example, if you have a vector of length 14 and it's an angle of 120 degrees, what are the components? What are the rectangular components of the vector? Well, v is length of v times cos theta by sine theta. That'll be 14 times cos 120 by sine 120. And okay, cos 120 is negative a half, sine 120 is root 3 halves. Okay, that times 14, you multiply 14 by each of these. 14 times negative a half is negative 7. 14 by root 3 over 2 is 7 root 3. So it's set negative 7 by 7 root 3, which you can also call negative 7i plus 7 root 3j. Some more examples. There's a vector from negative 2 by negative 1 to the point 6 by negative 2. What are the components of the vector from here to here? Okay, well, take the initial point and subtract the terminal point and subtract the initial point. So the x component is 6 minus negative 2, which is 8. The y component is negative 2 minus negative 1, which is negative 1. So the vector is 8 by negative 1. Okay, here's the length of, what is the length of the vector 3i minus 4j? Well, 3i minus 4j is a vector 3 by negative 4. Its length is the square root of the sum of squares. Root of 3 squared plus negative 4 squared. That's 9 plus 6, root 9 plus 16, which is root 25, which is 5, the 3, 4, 5 triangle. What is the length of the vector I minus j? Well, I minus j is 1i plus negative 1j, so the vector is 1 by negative 1. Its length is root of sum of squares, root of 1 squared plus negative 1 squared, root 1 plus 1, square root of 2 is the length. And here we're given two vectors, 3 by negative 5 and negative 2 by 3. The book asks, what's the vector 2u plus 3v? What's the length of v minus u? And what's the length of v minus v minus w? And what's the length of v minus the length of w? Here it's a sort of, I think it's a sort of a grammatical thing. Do we subtract and then take lengths, or take lengths and then subtract? We'll get two different results. All right. So here we go. V is 3 by negative 5, w is negative 2 by 3. So 2u plus 3v is 2 times 3 by negative 5 plus 3 times negative 2 by 3. First, we get rid of the scalar multiplications. 2 times 3, 2 times negative 5 is 6 by negative 10. Here, 3 times negative 2 is negative 6. 3 times 3 is 9. 6 by negative 10 plus negative 6 by 9. We add the x components, 6 minus 6. We add the y components, negative 10 plus 9. This comes up to the 0 by negative 1, or in other words, negative j. So that's this part. Length of u minus v. Well, we'll take the length of 3 by negative 5 minus negative 2 by 3. All right, so this we'll find, we subtract components. 3 minus negative 2 here, by negative 5 minus 3 here. That's 5 by negative 8. Its length is square root of sum of squares. root of 5 squared plus negative 8 squared. That's square root of 25 plus 64, square root of 89, and we're done. You can't go any further, I don't think. I think 89 is, I think it's a prime, so you can't really take on any square factors. Now, length of V minus length of W, what's that? Well, length of 3 by negative 5 minus length of negative 2 by 3. 3 by negative 5, its length is root 3 squared plus negative 5 squared. Length of negative 2 by 3 is square root of negative 2 squared plus 3 squared. This is root of 9 plus 25, root 34 minus root of 4 plus 9 is root 13. So root 34 minus root 13. And rest assured, this is quite different from this. Here we get a curious, this, okay. We have length V with length 25 at an angle of 330 degrees. What are the rectangular components of V? All right, V is length 25 times cos theta by sine theta. Cos 330 by sine 330. Cos 330 is root 3 over 2. Sine 330 degrees is negative a half. Times all that times 25 times both components is 25 root 3 over 2 by negative 25 over 2. Here's the answer to that. Now this one, let me see. Oh yeah, this is the hardest one and the longest one. This is an engineering problem or a physics problem. You have to use a basic physics rule of equilibrium. Here's a weight of 1,000 pounds. So it's a force of 1,000 pounds downwards. And here it's being held by two cables. This cable is at an angle of 25 degrees from the horizontal. This cable is at an angle of 40 degrees from the horizontal. What are the two forces? Well, this cable is pulling at 20 degrees upwards from the left with a force F1. This cable is pointing upwards to the right with a force of at an angle of 40 degrees from the right with a force of F2. Okay. And excuse me, and this downward force is 0 by negative 1,000. Now, okay, we use a basic rule of physics, which is that if a system is at equilibrium, then the forces add up to 0. Otherwise, this weight of 1,000 pounds would be accelerating in some direction. So, okay, since it's not, the forces add up. F1 plus F2 plus 0 by negative 1,000 is 0. Static equilibrium. Now, all right, this is at an angle of 25 degrees, and the supplement of that is 155 degrees. So F1 is F1 cos 155 by F1 sine 155. F2 has components F2 cos 40 by F2 sine 40 degrees. This vector plus this vector plus 0 by negative 1,000 equals 0. So this plus this, or this plus this minus 1,000 equals 0. F1 cos 155 by F plus F2 cos 40 by F1 sine 155 plus F2 sine 40 minus 1,000. This vector is the vector 0 by 0. And from this, we'll extract a 2 by 2 system. This x component is 0. This y component is 0. Oh dear. You know, I've made a stupid mistake, but we'll proceed anyhow. Oh dear. Let's see if I did this right. F1 cos 155 plus F2 cos 40, F1 sine 155 plus F2 sine 40 should be plus 1,000. That's a mistake. I'll have to correct it in the canvas. Let's see what we have here. This is page, which one is it? Which is this? 5-4, last page, equals plus 1,000. Okay, I'll have to change this to a plus 1,000. Now, this is a 2 by 2 system, and after a great deal of calculation, the usual 2 by 2 system calculation, you'll get that F1 is about 845.2 pounds and F2 is about 1,000 pounds, assuming I didn't this minus that I corrected this in the calculation. Well, okay, so that concludes that part.